All right, so separable differential equations. Um, a differential equation, we talked about this a little bit in the warm-up for slope fields, but a differential equation is an equation that contains some unknown function, y in terms of f, or f in terms of x. When we do our when we were taking derivatives, we would do implicit differentiation, and y was an unknown function in terms of x. So we're familiar with those terms. So a differential equation contains an unknown function y and one or more of its derivatives. So here's an example of a differential equation. Y prime is equal to 1/2 the quantity y squared minus 1 plus the second derivative, y double prime. So it contains an unknown function y and two different derivatives. The order of a differential equation is determined by the highest order derivative. So the example that we had just above, where it had the first derivative and the second derivative, that is a second order differential equation because its highest order is that second derivative. A function is a solution if the equation is satisfied when the function y and the subsequent derivatives are substituted into the equation. So if I were given a function y and I plugged it in to this equation we have up here, and I plugged in the first derivative of y, and I plugged in the second derivative of y, and it made the equation true, then that function is a solution to that differential equation. So I have this unknown function. Well, it's somewhat known because it's got a constant, but y is equal to x cubed, c times x cubed, some constant times x cubed. It is a solution. I want to verify that it is a solution to this differential equation. So I have x times y prime equals, or sorry, minus 3y equals 0. So I want to verify that this function here satisfies that differential equation. So I need y and I need the derivative of y. So y prime will be 3c times x squared. So y prime is going to be substituted in for y prime. Y is going to be substituted in for y. So I get x times 3cx squared. That was the derivative. Minus 3 times y, which was, that one's the y, c times x cubed. And I want to show that that equals 0. So now I just simplify this. This gives me 3c x cubed minus 3c x cubed. And what I see is, yes, that does in fact equal 0. So that means y equals some constant times x cubed is a solution to that differential equation. So what it's saying is any constant out in front is going to still work. So if I said perhaps y equals 12 x cubed, this is saying that that should be a solution to that differential equation. So this is a family of solutions because there are multiple values that constant can be. We can actually solve for a particular solution, not just a family of solutions. And what we need to be able to find the particular solution is we need an initial condition. A lot of times, your initial condition is going to look like f of 0 equals some number, or 0 comma some number, but it doesn't have to be. Most people think initial is at 0, but it doesn't necessarily need to be. I might know that the initial condition was -3, like I have here. So in the real world, that might be like, I like to go back to my roller coaster example. -3 might be 3 seconds before you get to the camera that's going to take your picture. And so it could be time and position. So 3 seconds prior to that, what was the position? That might be your initial information that is given. Okay. So it doesn't have to be 0, an X value of 0. This is often the case, but it is not required. It can be any point that I know that is on that particular solution. So if I take my family and I plug in the initial condition that I know, that means that y is 2, c times x is -3 cubed. I can solve for the c. So this gets me 2 equals -27 times c, which means that c is, divide both sides by -27. So my particular solution is y equals -220 over 27 times x cubed. That is the one function in this form, y equals c times x cubed, that will go through that point on the graph. So when I am solving for a particular solution, I need to have an initial condition, and that's going to allow me to solve for the constant. So we are going to be looking at separable differential equations. A separable equation is a first order. That means it's only going to have a first derivative, a first order differential equation. And dy dx can be factored as a function of x times a function of y. So we need to be able to separate the x's from the y's. And you're going to be separating them using multiplication. Okay. So here is my example of a separable differential equation. This is factored so that the x's and y's are separated from each other, because I could technically write this as 1 over e to the y times x plus 1. And division is multiplying by the reciprocal, so this is still considered factored. We're going to leave it in this form. So to solve a separable differential equation, what we need to do is separate the x's and y's on either side of the equation. So I'm going to have my y's on one side, including the dy, and my x's on the other, including the dx. So if I multiply both sides by e to the y and multiply both sides by the dx, I end up with e to the y times dy, because I multiplied by the e to the y dy. And then when I multiply both sides by dx, I'm going to have the x plus 1 times the dx. So I have now separated. This is why it's called a separable differential equation. I can separate the x's on one side and the y's on the other, and then I can integrate. So I'm going to integrate both of these. Now, if I do the integration at the same time, I can use just one constant of integration. So if I make sure that I do both of these integrals in the same step in my solving, I only need one constant of integration. It will count for both of them. So the integral of e to the y is e to the y. And the integral of x plus 1 dx, I should have said the dy on the other one, is x squared over 2 plus x plus c. So my constant of integration is happening in the same step, so that is covering the integral of e to the y dy and when I integrate x plus 1 dx. If I do them in separate steps, then I have to have different constants of integration. Now, the next thing that you need to do, once I have it in terms of, I have done the integration and they have the antiderivatives, now what I need to do is I need to solve for y. So to undo e to the y, I need to take the natural log of both sides or convert it from exponential to logarithmic. E is a positive number. Raised to any power is going to be a positive number. So I have to guarantee that I am dealing only with positive numbers, and I am also only allowed to take the natural log of a positive number. So unless I can guarantee that this is always positive, I need to have it in absolute value symbols. So I have separated my variables, integrated, include my constant of integration, and then solve for y. So now, if you wanted to find a particular solution given an initial condition, I'm going to give you that now. So we want to find the particular solution with the initial condition of y of 0 equals 2. Okay, so there are a couple ways that you can go about doing this. So I have solved at this point here. So my y value is 2 equals the natural log of the absolute value of 0 squared over 2 plus 0 plus c. So when I simplify, I get 2 equals the natural log of the absolute value of c. So when I convert from logarithmic to exponential, e squared, I don't need the absolute value symbol anymore because e squared will be positive. So this c is going to be a positive number. So that tells me my my constant. So that's one way that I can do it. The other way that I could do this process is once I had done the integration, I can substitute in now, because once I've done the integration, at that point, I can solve for there's the constant in the problem, so I can solve for it there. So if I substitute in the 2 for y and the 0 for the x's and simplify, I get that the constant equals e squared. So either way, you're going to come up with the same constant of integration. So my particular solution is going to be that y equals the natural log of the absolute value of x squared over 2 plus x plus e squared. So now, is x squared plus 2 plus x plus e squared, is that always going to be positive? So I can check. Oops, there. I can check x squared over 2. Oh, I'll do it this way. X squared over 2 plus x plus e squared. And then if I graph this, let's go zoom 6 and just see what I see. It's a quadratic. I feel that I have pretty solid evidence to state that x squared over 2 plus x plus e squared will always be positive because, like I said, let me change the window just so that you can feel more confident. Let's go to 100 and let's count by tens and graph that. Oops, I changed the wrong one. Gosh, doggone it. I want to change the y's. Count by 1 here. Change the y's from -10 to 100. Count by tens. Now I graph it. There we go. Again, what I'm seeing is that this is always positive. It is never going to touch the x-axis or cross the x-axis down into the negative region. So I can say, oops, I hit the wrong one. I can say that x squared plus x plus e squared is positive, which means that y will equal the natural log of x squared over 2 plus x plus e squared. So that is an example of solving a separable differential equation and finding a particular solution. Here is another separable differential equation. If you would like to try to solve this yourself, you know what? I'm changing my mind because this one has an interesting piece to it that we're going to talk about. Well, if you want to try to start it, pause the video and try to start it. And then there is an interesting little extra that comes out of this one that we're going to talk about. So the first thing that I'm going to do is I'm going to change y prime to dy dx so that I can separate them. So I want y's on one side and I want x's on the other. So to undo multiplied by y, I need to divide both sides by y. I can either write 1 over y times dy, or I can write dy over y. Most kids find it easier to see if I write it as that fraction out in front. And then I'm left with the 2x plus 1, and I multiplied both sides by the dx. So I got my y's on one side and my x's on the other. And now I'm going to integrate both of these. So when I integrate, the integral of 1 over y is the natural log of the absolute value of y. And I can integrate the 2x plus 1 dx at the same time, which gets me x squared plus x plus c. Because I did the integration in the same step, I can just use one constant of integration. But now I need to solve for y. So to solve for y, I need to convert from a logarithm to an exponential. So that's going to over here give me e to the x squared plus x plus c. And I don't need the absolute values when I convert my natural log into an exponential. The y is on that side. I don't need the absolute values because e to any power will be a positive number. So I don't need the absolute values to say y is for sure positive because it has to be. Now, using our exponent rules, x squared times x cubed is x to the 2 plus 3. When I have addition in the exponent, I had multiplication with like bases. So I'm going to rewrite this. So if you got it to this point, good job, but I want to show you something different here. I'm going to rewrite this as e to the c times e to the x squared plus x, because constant c is a constant and e is also a constant. E is a number. E to the x is not constant, but e to a constant is. So what this gives me right here is a new constant. So what I'm going to do is I'm going to rewrite e to the c, and I'm just going to give it a new letter so I don't have as complicated of a constant. So what I get here is y is going to equal k times e to the x squared plus x. So I now have just a singular constant instead of a number to a constant, and I don't need the constant added at the end of those x's. So now if I wanted to find the particular solution, with initial condition, again, let's do y of 0 equals 2. If you want to try to solve for that constant now, and now remember, our constant, we have changed the way it looks, but a constant raised to a constant power is still a constant. So we don't need two constants. We can just write it as 1. So we're now solving for k. So if you want to try that, pause the video and go ahead and try to solve for k. So when I plug in my y value of 2 equals k times e to the 0 squared plus 0, I get 2 equals k times e to the 0, and e to the 0 is just 1, so k times 1 is just k, which means our constant is 2. So now my particular solution is 2e to the x squared plus x. Y equals 2 times e to the x squared plus x, which is a little easier than trying to solve for that constant up in the exponent. And 2 is a much nicer constant than e to some weird number that's going to get me a 2. So when everything feels like it's going well and we're understanding it, yay, let's introduce trig. So now I want to separate this in terms of x and y. And you're like, well, I don't see an x and a y. That's because there isn't one. But I can factor it in terms of secant y times 1. And I can integrate 1. So if I'm going to separate this, I can have 1 over the secant of y times dy, and I have over here 1 times dx. Now, 1 over secant y is not fun, but it is secant y is a reciprocal function, so 1 over secant y is actually just cosine y dy, and here I have 1 dx. So now I can integrate that. The integral of cosine of y dy is sine y, and the integral of 1 dx is x plus c. And since I did the integration in the same step, I only need one constant of integration. So now I need to solve this for y. So y is going to equal the inverse sine of x plus c. The other way I could have thought of this, dy dx equals secant y, again, times 1. I could have started right away by saying dy dx equals 1 over cosine y. So now when I multiply both sides by cosine y, and I multiply both sides of cosine y dy, and then I multiply both sides by dx, I get to the same place that I was when I divided by secant y. Divided both sides by secant y. So the initial condition is a y of 1 equals 3. And I have a differential equation, dy dx equals negative x over y. So this one has something also that we're going to need to be careful of. And here's where kids are going to make a mistake. So if you want to try, what I would like for you to do is separate. This is separable. So separate the x's and the y's and then integrate and then unpause the video and see if you did that correctly. And then there's one additional thing I want to show you with this problem. So I get y dy equals negative x dx. And when I integrate, I'm going to get y squared over 2 equals negative x squared over 2 plus c. So when I multiply everything by 2, I get y squared equals negative x squared plus 2c. I have to do the operation to the c because this c has to be the same value all the way through the problem. Now, some instances I have seen kids go, this is C1, and then they will call this one C2 and define C2 to be 2 times C1. But that's a lot of extra writing. I don't see any reason to do that when it's just as easy to multiply that constant by a number. At the end, if I need to, at that point, I will redefine it. But every time I do an operation, if I'm redefining the constant, I might have to do it 2 or 3 times in the problem. So I'm just going to wait until the end and then redefine that last constant in terms of just a c. So now, again, I need to solve for y. So I need to take the square root of both sides, and when I solve by taking the square root, I need to include the plus or minus. And here's where kids are going to get in trouble. There's a couple things that are going to happen. One, you're going to forget the plus or minus. Or two, you're going to forget that you have an initial condition that you have to guarantee you get correct. My initial condition says that when x is 1, y must be positive 3, not plus or minus 3. So, because of the initial condition, we are only going to look at the positive square root due to the initial condition. Okay. So now I need to solve for that constant. I am going to suggest it's not a lot of fun to have to get that constant out from underneath the square root. So I'm going to actually use this portion, the y squared equals negative x squared plus 2c, to solve for my constant. Okay. So when y is 1, x is, sorry, I did that backwards. When y is 3, x is 1. Now here's the other mistake some kids are going to make. The negative is after the squaring has happened. It is not just because the negative is on the number and it's squared automatically a positive. If I wanted it to be that, then that's when it's square including the negative, but that's not what I have. The negative is outside of the squaring. It is not included inside. So what I get is 9 equals negative 1 plus 2c. So 10 equals 2c. Now, a lot of kids are going to, because you're good math students, we are going to solve for c, and we get that the constant is 5. But in my particular solution, y equals the square root of negative x squared plus, that's my constant that I'm replacing. I could have stopped here and replaced it with the 10. If I didn't, and I went y equals the square root of negative x squared plus 2 times c, which I got was 5, I now need to simplify, which is the square root of negative x squared plus 10, which is the same thing I got when I recognized this is the constant that I am solving for.